3, 2, 1, 0. Ignition. Liftoff.
Good evening, astro lovers, far and wide. Welcome to another night at the observatory. Tonight we're going to start the night at the observatory special a little bit differently. As you can see, we're out here at the Mount Dandenong Primary School, which was hit pretty hard with the storms that came through last week. We realised at Mount Burnett we were very lucky to get through the storm unharmed and unscathed, but many of our members were affected. They were without power, some still without power, and many people in the community are still heavily affected without access to things like clean running water. It's a terrible event, and even while we're out here today, it's pretty hard to sort of come to terms and actually believe what we're seeing. It's really like a natural disaster. So we wanted to start tonight by thinking about some of the ways that we might be able to give back to the community. And one of those ways is we're going to put a link up on the screen, and we'd love for you to make a donation if you can, big or small, to the Emerald SES. They do fantastic work. Unfortunately, one of their vehicles were damaged as part of the storms and in their response to those events last week. And they need that money for training and equipment. So if you can, we'd really appreciate it if you could, instead of donating to MBO tonight, make a little donation to them. We'd love to then give back to you for making a donation, and one of the ways that we're looking at doing that is by potentially setting up a COVID-safe night at the observatory in person. We'll get a few coffee trucks and maybe a donut van, so if you've got the ability to help us out with that, reach out via our Facebook or our email info@mbo.org.au. We'll get the community together, try and take our minds off some of the terrible things that have been going on. I know it's hard, but I think it's really important, and so does the rest of the team, to try and give back to the local community in whatever way we can. We're really sort of struggling to come to grips with it, and we're thinking of all of you, and hopefully these events that are going to come up will be a way of sort of getting back together as a community and taking the time to do that. So once again, if you can, make a donation and enjoy the rest of your night, and we'll see you soon.
While we are all joining this event from our own location, we would like to acknowledge that we are meeting on the lands of the Wurundjeri people and the Boon Wurrung people of the Southeast Kulin Nation. We would like to pay our respects to their elders, past, present and emerging, and to all First Nations communities joining us today. Welcome everyone, either from Australia or overseas, to another night at the observatory. Tonight is our 9th stream, and it is a voyage about galaxies. We advise you that if you have a big screen and are able to watch this segment on it, please do so. But before we begin, I'd like to give a shout out, as always, to our fabulous crew who are working hard behind the scenes and are on Facebook and YouTube tonight. They too play a big part in bringing this production to you. We also have Adam, who is my technical operations person for the evening. I'd now like to introduce you to our panelists who will be presenting this evening. Could you please join me? Andrew? Drew?
G'day all. How you going?
Ella? Stuart? Merv? Jamie, and Steve. And of course, myself, Petra, who will be your host for this evening. So let's get started. And first up for tonight's show, I will be explaining to you the different types of galaxies. Okay, so we know there are galaxies and that we're in one. A galaxy is a huge collection of gas, dust, and billions of stars and their solar system, all held together by gravity. All galaxies are made up of these same things. The light that we see from each of these galaxies come from the stars inside it. However, they come in many different shapes and sizes: spiral galaxies, elliptical galaxies, and irregular galaxies. This is a spiral galaxy known as M83, also known as the Southern Pinwheel. It lies in the constellation Hydra and is about 15 million light years away. It is both relatively large and bright in the sky, making it a frequent target for both amateur and professional astronomers. Spiral galaxies have a flat, spinning disk with a central bulge surrounded by spiral arms so they look like giant pinwheels. The arms of the pinwheel are made up of stars and lots of gas and dust. Gas and dust are some of the main ingredients needed to form new stars. Young stars burn much hotter than older stars, so spiral galaxies are often some of the brightest in the universe. About 20% of all galaxies are spirals. Our home galaxy, the Milky Way, is a very good example of one. Here you can see a trio of galaxies, sometimes called the Draco group, located in the northern constellation of Draco. The middle galaxy is smooth and oval-shaped, and this is an elliptical galaxy. Elliptical galaxies are shaped like stretched-out circles or ellipses. Some elliptical galaxies are more stretched out than others. One might look almost perfectly circular, as in this image, because they're in a form like a ball. Another one might look long and flat. Elliptical galaxies contain mostly older stars. That means they often aren't as bright as spiral galaxies. They also have very little dust and gas. Elliptical galaxies are the largest and most common galaxies observed. They make up about 60% of all galaxies. There are two other galaxies in this image. The galaxy on the left is a spiral galaxy, but we can only see its edge, so it's known as an edge-on spiral. And the galaxy on the right is also a spiral galaxy, but we can see it face-on, so it is known as a face-on spiral. The beauty of this image is that it illustrates that spiral galaxies are flat and elliptical galaxies are ball-shaped. While this group is far too small to be a galaxy cluster, and they have not been catalogued as a compact group, these galaxies all do lie roughly 100 million light years from planet Earth. And there are also galaxies that aren't spirals or ovals. They have irregular shapes and look like blobs. Irregular galaxies are just that, irregular. They don't have a single common shape. Irregular galaxies are among the smallest galaxies scientists have observed. However, they can also be very bright. Like spiral galaxies, irregular galaxies are often filled with gas, dust, and lots of bright young stars. About 20% of all galaxies are irregular galaxies. This image is of the Dwarf Galaxy, NGC 1569, and is apparently undergoing a burst of star-forming activity, thought to have begun over 25 million years ago. The resulting turbulent environment is fed by supernova explosions as the cosmic detonations spew out material and trigger further star formation. This galaxy is only 11 million light years from planet Earth, so this relatively close starburst galaxy offers astronomers an excellent opportunity to study stellar populations in rapidly evolving galaxies. This galaxy lies in the long-necked constellation Camelopardalis. A really good way to remember galaxies and how they are shaped is Spiral galaxies are fried eggs. Elliptical galaxies are boiled eggs. And irregular galaxies are scrambled eggs. You're never going to look at eggs the same way again. Thank you for watching. And our next presenter will be Drew, talking to you about what galaxies are and our galaxy.
Thanks, Petra. Welcome to my presentation tonight. I've got a nice picture here of the sky full of stars. If we have a nice, clear, dark night, we can see many of them. We can't often from the city, which is why we invite you, when we can all do so, to come and join us out at Mount Burnett with a darker sky. Most of the light we see in the sky are stars, but not everything. Here's a couple of photos of a couple of galactic clusters. These are clusters of galaxies a long way away from us. Here on the left, we've got a Bell 370, and on the right, a Bell 1689. These galactic clusters are named after Georgia Bell, who did a lot of work with galactic clusters. But these are a long way away. Perhaps we can find some galaxies a bit closer to us. Here's that picture I was showing you just before, and it's a beautiful night with the sun just having set. But there's more than just stars in the photo. If we look here, we can see this big patch of what looks like thick cloud across the sky, and that's actually a galaxy, in fact the closest galaxy to us. In fact, the galaxy that we're in, the Milky Way. Now, whilst that thick band is the main body of the Milky Way, which stretches all around the sky in a loop around us, all the stars that we can see with the naked eye are actually within our galaxy. We can't see or photograph the entire Milky Way because we're inside it, but we can see other galaxies similar to it. This is one I've chosen, NGC 2608. It looks a fair bit like our galaxy. It's a spiral, as Petra was describing, and our galaxy looks a bit like that. Andrew will show you a few more pictures in redshift of our galaxy a bit later. Here's another picture of a galaxy a fair bit like ours, although this one's a fair bit different. This is NGC 3254, and this picture was actually shared by NASA about a week ago. This is actually quite a special one because this is an example of what's called a Seaford galaxy, where the central core area is very luminous. If we were looking at some wavelengths of light, it would be blinding looking at that central area. That central area of this galaxy is actually brighter than most entire galaxies, including our own. Now let's come back to Earth for a bit. Here's a nice picture including Aurora Australis, or the Southern Lights, you can see down here. They're very beautiful, but we're not actually talking about Aurora tonight, we're talking about galaxies. We can see, if we look on the left of the screen, the Milky Way again in this photo. And if we look on the right of the screen, we can see what appears to be a couple of clouds. They're not actually clouds though, they're actually galaxies very close to ours in the universe. They're the Large Magellanic Cloud and the Small Magellanic Cloud, but if you're not careful when you're looking at the sky, you'll see them and just think that they're clouds. Let's have a bit of a closer look. Here's the Large Magellanic Cloud, and it looks a fair bit different when you look at it a bit closer up. And the Small Magellanic Cloud. And the Small Magellanic Cloud is photographed there with 47 Tucanae, which is a star cluster, which we'll be very happy to show you, and our telescope operators usually do when people are able to come out and visit us at MBO. Now, the LMC is the larger of the two and is estimated about 1/10 of the mass of the Milky Way, which is a fairly big one as far as galaxies go. These two sit there apparently serenely in the sky, but in fact there's a bit of a fight going on. The Large Magellanic Cloud is pulling gas away or eating the Small Magellanic Cloud, and in turn it's being eaten by the Milky Way. Now, we thought that they were just satellites orbiting as we spin in the sky, but it turns out they're moving a fair bit faster than that, and eventually they'll either get eaten by the Milky Way or, more likely, escape from its grasp and drift away. Now, here's another photo of an aurora, and you might be confused thinking that I'm all about auroras tonight, but this one's the Aurora borealis, the northern lights, which can be seen from the northern hemisphere. And you can see the aurora very brightly. I'll just point it out in case anybody's having a little bit of trouble seeing it. But again, that's not the key thing I'm here to show this photo for. We've got this little smudge in the sky here, and that little smudge is actually a galaxy, the Andromeda Galaxy. It's quite similar to the Milky Way, but a bit bigger. Let's have a closer look at it. I'm not going to tell you too much about the Andromeda Galaxy because Ella will tell you a lot more about it later. But it's another galaxy in the local group, and Andromeda and Milky Way are the two big members of our local group here. And just like the Milky Way has some satellite galaxies and the two Magellanic Clouds, Andromeda has satellite galaxies as well. Eventually, Andromeda and the Milky Way are going to collide, like these two here, which in this photo are NGC 2207 and IC 2163. And I'm sure that Ella will tell us a bit more about that as well. So, thank you for viewing my presentation and enjoy the evening.
Thank you, Drew. It is always nice to visualize our galaxy and our neighboring galaxies. Okay, so next up we have Jackie. Jackie will now give you details about the Milky Way and its features.
Mount Burnett Observatory is a community-run astronomical society in the Dandenong Ranges. We are completely volunteer-run and have over 500 members. We focus on community engagement, outreach, diversity, and helping our members to get the most out of their love of space and astronomy. The observatory was originally built by Monash University for students to do astronomical research, especially on variable stars whose brightness changes over time. Over the next 2 decades, the site was expanded and upgraded, but eventually took a back seat to modern giant internet-connected observatories around the world. In 2011, our 5 founding members reached an agreement with the landowners and took over the lease and established the society. Now, we run over 80 events each year, including members' nights, public viewings, and special events. We have several special interest groups including deep sky observing, radio astronomy, astrophotography, astro arts, and young observers. In 2020, we expanded our online presence and now host regular live streaming events. We welcome all new members and love making new friends with other astronomy lovers. You will be joining a friendly community of passionate, hard-working amateurs who have a grand vision for the future of the observatory. We hope to see you up at MBO soon.
Where is the Milky Way? Where do you look for it in the sky? How do you find it? What does it look like? Well, one place not to find it is near the moon, and it's actually best not to look for it when the moon is in the sky. So wait for the moon to set, or have a moonless night. It's also best to get away from light pollution. So if you've got lots of street lights nearby, it's best to move away from them. So it's also good to turn off any lights you have on the outside of your house, and maybe even the inside as well. These will affect your eyes and make it very hard for them to open up and see the faint light in the sky that's coming from the Milky Way. And it's also not that good for your body at night. Your body needs the darkness at night as well to be healthy, and it's just not going to help you see the Milky Way. So turn them off. If you must have a light, some red light is best, and getting away from the street lights is also very good as well. And it makes the stars disappear. The sky looks a bit grayer, and you might only see 1 or 2 stars up there in the sky. So turn off those outside lights, maybe the inside ones as well. Turn them down. Move away from the street lights. Choose a moonless night, or at least a night where the moon has set. And then the next thing to do is to wait for your eyes to adapt to the dark. So our eyes are made for bright daylight, but they can open a little bit wider in the dark. It takes at least 10 minutes. Best to wait for 20. And they open a couple of more millimeters. I mean, they're not as good as owls or cat's eyes, which open much, much wider. But a couple of millimeters helps. If you have a nice clear sky above your head, you might see something like this. A bright band of light stretching across the sky with what we call the star clouds of the Milky Way shining down. They sort of make star clouds because there's so many stars there, they just all blend together. The dark patches in front of them are clouds of dust and gas blocking the light off behind them. So we have a very famous one here with the Southern Cross, the constellation that's on our flag, and this little patch here is known as the coal sack. So that's one patch of dust that's blocking off some light. Here we have the pointers pointing the way to the Southern Cross, and you'll notice it looks a little bit, humps over a little bit here and is flat there. This is because we're slightly above the centre line of the Milky Way, so we're looking at the central bulge of the Milky Way here, but we can't see the bulge on the other side because it's being blocked by the disk. When the centre of the galaxy is rising in the east, it looks like it's standing upright in the sky. We can see the constellation Scorpius here, with his long curving back and his fish-hook tail curving around. And the other constellation we look for is Sagittarius, just marked by this teapot shape. So there we go, there's the spout there, and he has the lid on top. And the centre of the Milky Way is kind of pointed at by the teapot shape there. When the centre of the galaxy is setting in the west, as it does in the evening sky around November, it lies horizontal to the horizon we can see Scorpius here with his tail now standing upright in the sky. In this picture we have what we call the summer Milky Way in Australia, but we're looking the opposite way from the centre of the galaxy. We're looking out towards the outer edge of the galaxy, so it looks a bit thinner here. And we have a very famous constellation, Orion. We can see Orion here. Just draw him out. There we go. So we can see Orion's belt across there. He's got his sword. You might know Orion as the Saucepan. We have Sirius here. We have Taurus, the Bull, and another very bright star, Canopus, as well. Sirius is the brightest star in the sky, and Canopus is the second brightest star. When Orion sets in the west, as he does in the autumn skies in the evening, the Milky Way is standing upright again, and he looks like he's lying down on his side. So we often see the Milky Way stretching across as a band of light. Occasionally we see it sitting all around the horizon, because we're just about at the right latitude, close to 30 degrees south to see that. But if you do want to see it, you do need to get away from the city lights and suburbia on a moonless night and give your eyes a little bit of a chance to adapt to the dark.
Thanks, Jackie. It's nice to learn about what stars we have in our Milky Way. Excuse me. So I'm just going to make a couple of announcements before we continue. As some of you may already know, we've had a bit of technical difficulties tonight, one being that Facebook isn't working for us for our live streams. But that's okay, we're still on YouTube. So if any of you in YouTube are popping into Facebook, could you please let everybody know on there who's looking for us to please come over to YouTube? That would be great. And secondly, don't forget, if you have any questions tonight, pop them into the comments and we'll attempt to answer them. There is also a Planisphere giveaway for the question of the night. We now have Andrew showing you on Redshift the Milky Way.
Good evening, all. We'll take you on a bit of a space flight and have a look at the Milky Way from an angle that we can't possibly do in just a few moments. Okay, this is, thanks to Redshift, of course, for allowing us to use their software to let you see all this. As Jackie said, you need the moon out of the way. So if you were to have a look tonight, Melbourne is not really good for viewing, but perhaps somewhere else around our viewing area, you might be able to see a clear sky, but it's not a good night for it because the moon is in the sky and lighting up the sky because it's pretty close to about a 3/4 moon. Monday might be a better time. Certainly in Melbourne, the weather will be better and the moon will be further away from the Milky Way, and so you might get a better look. In 2 weeks' time, even better, because the moon will probably not be up at all. Now, this is a bit of a view similar to what Jackie was showing you. And we can see the Milky Way stretches from the east up overhead. And then if we go a bit further around, it is almost directly overhead. Here's the Southern Cross. Sorry, we read that. Southern Cross here. So you can see the Milky Way virtually is a background to the stars of the Southern Cross. And we're going to
Okay, folks, we seem to have lost Andrew in redshift. I think it may have just swallowed him up like a galaxy does. Okay, that's fine. We can come back to him later. So next up, we'll move on to Ella. And Ella will be speaking to you about Andromeda.
Hang on.
I know, Andrew's back. I thought you got swallowed by the Milky Way, Andrew.
Oh, did I? Oh, I wasn't even aware of that. Sorry.
But you're back.
Where did you lose us? Oh, it doesn't matter. We'll move on.
We'll move on. Please do so. You froze, and I went, oh, he's definitely gotten lost in the Milky Way. Oh, he's gone again. How about we just go to Ella, and we will get back to Andrew when he comes in. Hello, Ella. Come in and tell us all about Andromeda, our neighbour.
Yes, hello, everybody. So I'll just get the video up. My name is Ella, and this evening I'll be taking on a space journey all about the Andromeda Galaxy. Of all the galaxies that we can see in the night sky, the Andromeda Galaxy, also known as M31, is the easiest and most impressive to observe. Not only is it probably the most famous galaxy out there, apart from our very own Milky Way galaxy, this spiral galaxy is thought to be slightly larger than ours, and lies 2.5 million light years away, meaning that it's one of the most distant objects visible to the naked eye. From a dark sky site, the Andromeda Galaxy is easy to see without a telescope or binoculars. A telescope will show you as an ellipse of light, accompanied by two smaller patches of light. These are the galaxies called M110 and M32. The Andromeda Galaxy is one of the galaxies in our local group, which is a small collection of around 30 galaxies, which includes our very own. Andromeda can be seen in our sky, the southern hemisphere, in October to November, and to find her, you'll need to look lower in the horizon. Andromeda consists of several strings of relatively faint stars, meeting at the Alpheus, its brightest star on the corner of the square of Pegasus. It contains little of interest to the amateur astronomer, and owes its fame almost entirely to the Andromeda Galaxy and its satellites. Its diameter is almost approximately 200,000 light years and shares various characteristics with the Milky Way system. Princess Andromeda lies at the heart of a story that encompasses many constellations in the northern sky. According to Greek myth, she was chained to a rock and offered as a sacrifice to the sea monster Cetus, in atonement for the boastfulness of her mother, Cassiopeia, the wife of King Cephas. The hero Perseus, flying home after slaying the Gorgon Medusa, came to Andromeda's rescue, swooping down in his winged sandals and using Medusa's head to turn the monster to stone. Ancient sky gazers have probably pondered the nature of this blurry spot for many thousands of years. However, the oldest known discovery of the Andromeda Galaxy dates to 964 AD, when a Persian astronomer named Abd al-Rahman al-Sufi wrote a book about fixed stars. He called out Andromeda and also noted the position of the large Magellanic Clouds, a more petite satellite galaxy of our Milky Way. The Andromeda Galaxy was referred to as a small cloud in the heavens. Did you know that? It wasn't until the 1800s that astronomers started realizing just how special Andromeda was. That's because until roughly a century ago, scientists thought our Milky Way was the entire universe. For some time, observers using their telescopes to hunt comets have been turning up nebulae, a term that describes basically any fuzzy night sky object that was not a comet. Ones with spiral arms, like Andromeda, were called spiral nebulae. In 1864, an English astronomer named Sir William Hudgens used a prism to break apart and analyse the various colours of light from a variety of nebulae. When he did, Hudgens noticed that the light spectra of M31 was very different from the other nebulae that he had seen. For centuries, astronomers regarded the Andromeda Galaxy as a component of the Milky Way galaxy, i.e., as a so-called spiral nebula, much like the other glowing masses of gas within the local galactic system. Only in the 1920s did the American astronomer Edward Powell Hubble determine conclusively that the Andromeda Galaxy was in fact a separate galaxy beyond the Milky Way. The Andromeda Galaxy has a past involving collisions with and accretion of other galaxies. Deep surveys of the outer parts of the Andromeda Galaxy have revealed huge coherent structures of star streams and clouds, with properties indicating that these include the outer remnants of smaller galaxies, eaten by the giant central galaxy. An interesting fact about the Andromeda Galaxy is that in a discovery it was determined that M31 had two nucleuses. An image revealed by the Hubble Space Telescope shows a double nucleus with two stellar concentrations and one slightly brighter than the other. However, the Hubble determined that it is the dimmer nucleus that is the true controid of the stellar distribution, with the brighter nucleus off-center with respect to the outer isophotes of the galaxy. It is possible that the brighter concentration is either a remnant of a galaxy recently eaten by M31, or is a captured star cluster. The Andromeda Galaxy is a giant swirl of around 1 trillion stars just down the street from the Milky Way. But billions of years from now, it will collide with our very own. Computer simulations derived from Hubble's data show that it will take an additional 2 billion years after the encounter for the interacting galaxies to completely merge under the tug of gravity and reshape into a single elliptical galaxy, similar to the kind commonly seen in the local universe. Although the galaxies will plough into each other, stars inside each galaxy are so far apart that they will not collide with each other during the encounter. However, the stars will be thrown into different orbits around the new galactic center. Simulations show that our solar system will probably toss much farther from the galactic core than it is today. To make matters more complicated, M31's small companion, the Triangulum Galaxy, or M33, will join in the collision and perhaps later merge with the M31 Milky Way pair. There is a small chance, though, that M33 will hit the Milky Way first. But you have nothing to worry about right now. We have much larger problems on our very own planet to worry about rather than a giant galaxy ploughing into us. On this note, I hope you learned a lot more about the Andromeda Galaxy and its incredible features. I hope you all had an amazing evening and you have a great holidays. Good night.
Thank you, Ella. It's nice to know that Andromeda won't cause too much trouble when it collides with us in the Milky Way.
Yeah, not anytime soon at least. We're
Yes,
good for now.
that's really good to know. Yes. Okay, so thank you, Ella. I would just like to remind everybody that tonight we are asking everybody to give some donations to the Emerald SES, if you can. This is the website that you can go to put your donations in. They need about $30,000 a year just to keep their rescue trucks on the road. That's just for their rescue trucks. Nothing else that they, other than whatever else that they do. And they do so much more, as we all know. So if everybody could dig deep in their pockets tonight and give to the Emerald SES, that would be fantastic. Thank you. So next up we have Stuart describing the structures of galaxies with his awesome diagrams.
Yep. Hello, everyone. Yeah, I thought I'd get into some of the finer details of the structure of galaxies. Yeah, so there's a few different types of galaxies out there. There's ellipticals and irregulars, and of course spirals. But the ellipticals, they're too orderly for me, a bit boring. Irregulars, they don't really have too many points of interest. They're too chaotic. So I'll be focusing mostly on our favorite spiral galaxy, the most iconic. So yeah, here we go. The spiral galaxy, it has three main components. It has the central bulge, the disk, and the halo. You might not have heard of the galactic halo. It's a bit less known because it's not easily visible. It's not really visible in any of the pictures that we've got. It's just another component where very sparse amount of matter flies around everywhere. One of the components you'll find in the halo are globular clusters, large clusters that just kind of orbit the galaxy haphazardly. And the other major objects you'll find in the halo are remnants and scraps of galaxies that merged with the Milky Way. And on that note, there's some galaxies that haven't quite got that far, the satellite galaxies that orbit around the Milky Way. Every decent-sized galaxy has a whole bunch of satellite galaxies that kind of orbit around. The Milky Way has a fair number of them, 15 or something, around that number, I'm not too sure. And if they get too close, well, they might become dinner. But so that's the kind of outer skirts of the galaxy. And everything you see on the diagram at the moment, that all composes about 1/5 of the total mass of the galaxy. So where's the other 4/5 of the mass? Well, it's dark matter. And where is dark matter on this diagram? Well, you'll find it, it's somewhere on that diagram. We're not entirely sure. Well, we do have a good idea that if it's part of any of those components, it will be a part of the halo. It's kind of spherically distributed around our galaxy. But we can't see it. So there's still active research into how it's actually structured on a smaller scale. So you might have noticed that the halo and the bulge, they're spheres, and the disk of the galaxy is disc-shaped. These shapes kind of appear all over the place when you start looking at things in space. And there's a reason for that. It's because they all follow the laws of physics. So when you think of an object in space that's spherical, probably the first thing you'll think of is a planet or a star. Those are spherical because gravity pulls everything together. And if you have something really tall, then it's just going to get pulled down and flattened out. I dub these objects heavily interacting matter because they're physically attached to each other. This isn't why galaxies have spherical components in them. That's kind of on the other side of the spectrum, with matter which doesn't interact with itself, like stars. Stars just little balls of fire, and they fly past each other without too much care. They only really interact through gravity, and that kind of holds them together in a rough ball shape. But apart from that, they're kind of traveling all in every direction randomly. That's kind of the structure of the bulge at the center of the galaxy and the halo and the globular clusters. Those are the spheres, but what's with the disk? Well, the disk is kind of in the middle, I like to think. It's not strongly interacting, physically connected to each other. It's not weakly interacting. The stuff that makes up a disk in space slightly interacts with itself. And the other important component is that it's spinning. So in the case of a spiral galaxy, that's the disk is formed from gas and dust. Gas and dust interact with themselves, they drag on each other. So if you imagine a gas cloud that's orbiting up and around, then it's going to have to punch its way through the disk. That's going to slow it down, and it will have to keep on doing that until it's slowed down enough that it's just swept up with the rest of the disk. So you need a bit of interaction to get a disk, but yeah, that's just how those fluids naturally form. So yeah, let's go back to the structure of a galaxy. The disk, the next component we'll talk about, is flat and circular. But if we look at it from above, it does have these regions that are more dense than elsewhere, these spiral arms. They're very iconic. And they look a bit windswept here. And so you might think that they move around the galaxy like this in a simple rotation. And you'd be pretty much right with how that works. There's a bit of more complicated dynamics going on that they might undergo, but for the most part, that's pretty much correct. They just rotate around the galaxy like you'd expect. just over a very long time. But the rest of the galaxy doesn't rotate like that. I'll just put on the orbits of some of the stars that orbit around this galaxy, and you'll notice that these orbits will take a different amount of distance to get around the galaxy, and thus it'll take the stars a different amount of time to travel around the galaxy. So if we follow them around, we notice that they very quickly disperse. So in actual case, there's no way that these spiral arms are physical objects or clusters of set stars, because if we just think of them like that, then they'll quickly disperse, and the inner sides of the spiral will quickly wind up much quicker than the outside. It's called the winding problem. And so our current understanding of what these spiral arms actually are is, scientists call them density waves. While the stars travel through the spiral arms, they kind of clump together, and as they exit, they spread out. And yeah, I've had a rough attempt at demonstrating this, though I might be coming up against the limits of PowerPoint. It's finally failed me. It's not entirely clear, but the stars are slightly closer together in the spiral arms, and I got that effect by slightly altering the orbits that they take. But I hope to communicate that it's actually quite a complicated and nuanced process, the gravitational interactions of everything with everything else. It's actually quite complicated, so much so that we don't quite know all the details ourselves. This might be how stars are affected by it, but there's also gas and dust and other components that are also part of these spiral arms. And it's actually something that we're still researching, how spiral arms work. So yeah, I mentioned that the gas and dust kind of were the first things that formed the disk of the galaxy, and that's the reason why the majority of the gas and dust in a galaxy, in a spiral galaxy, is in the disk. And gas and dust is also the primary ingredient to forming stars. That's what forms stars, when you have lots of gas in one area and then it collapses in on itself. And even in the disk, we have our regions of extreme density in these spiral arms. So you'll find that the majority of the star formation in a galaxy occurs within the spiral arms. And yeah, stars have a bunch of different colors, but the brightest stars on average are blue. And a price comes for being the brightest stars. It means that they burn out relatively quickly. So where stars form, the bright blue stars are created, but they quickly burn out. And when I say they only live for a short amount of time, I understand that I, as an astronomer, have a bit of a warped idea of how long time is. Other people might have other opinions and say that seems like a long time, but I think we can all agree it's a pretty short time. Blue stars usually only exist for a few million years. So yeah, not too long. I think we can all agree. I mean, a few million years, that's a pretty quick amount of time. Well, it definitely is for galaxies, at least. Galaxies, for the most part, have been around for 10 billion years. So if you imagine that a human was living the life of a galaxy, humans live, let's say, around 100 years. So if a human was a galaxy, then a bright blue star would only exist for half a week. So in the lifespan of a galaxy, these blue stars don't live for a long time. They don't even have enough time to orbit out of these spiral arms before they stop shining. So so blue stars are actually intrinsically linked with regions where stars are actively being formed. And that's why the spiral arms of most spiral galaxies are blue, because they have these bright blue stars. And if you see a blue region in a galaxy, there is active star formation occurring there. So let's go to our last middle component of the galaxy, the galactic bulge. And you'll notice that it has a yellow color, which indicates to us that there isn't active star formation occurring in the middle of the galaxy anymore. because once the blue stars burn out, the next prominent color that stars are is yellow. And yeah, so there's not too much interesting to say about the bulge. Like I said before, it's kind of a sphere of stars that are all moving in their own directions. But there is one interesting thing to look at. So let's zoom in. What have we found here? It's a supermassive black hole. These are singularly impressive objects in the galaxy. Nothing really compares to them. We like to measure things in space in terms of how many suns they weigh. Our sun is 1 solar mass. The largest stars that we've been able to discover are a few hundred solar masses, so nothing to be scoffed at. They're pretty large, but our supermassive black hole is a few million times the mass of the sun. It's really in a league of its own. There's no other single object in the universe like a supermassive black hole. And so you might mistakenly think that the galaxies orbit around supermassive black holes. They're immensely huge, and they're at the center of a galaxy. But that's not actually the case. So a supermassive black hole might have a few million solar masses. We've actually found a few that have a few billion, but there are a few hundred billion stars in our galaxy. So the supermassive black hole, that's only a few million times the mass of the sun. There are 100 billion stars, and then a whole bunch of other stuff, and dark matter on top of that. All in all, our whole galaxy, we think, comes to a total mass of 1 trillion times the mass of the sun. That's a million times the mass of the sun, 1 million times larger than the supermassive black hole. So in actual fact, the supermassive black hole, as big as it is still an absolutely minuscule part of the galaxy. Its gravity shouldn't really affect the stars outside of those that are just in its local environment. That said, though, it does seem to have some effect. The mass of a black hole seems to have a strong correlation with some strange properties of galaxies, such as its rotation rate and its star formation. It's becoming clearer that supermassive black holes do have an integral link to the overall dynamics of a galaxy. And we're not entirely sure of all the processes that relate to all these different things. If you haven't guessed already, galaxies are incredibly complicated systems. They have lots of different things going on. They're probably some of the hardest things for scientists to simulate and understand because of the absolutely enormous different scales that are going on within them. We have these supermassive black holes, which are absolutely tiny compared to them, but they seem to have some incredibly strong effect on the overall dynamics. So yeah, galaxies, despite 100 years of research, are still very much at the forefront of science. And yeah, keep an eye out for all the incredible, beautiful things that we have yet to discover about them. Thank you very much.
Thank you, Stuart. I love your diagrams. They always explain things so well. All right, so I'm now going to welcome back Andrew. Come on in, Andrew. And Andrew is going to talk about, yep, fingers crossed, that's right, about our Milky Way on Redshift. Thank you, Andrew.
Thanks, Petra. Let's hope my internet doesn't let me down again. Sorry about that hiccup before. Right, here we are again. We'll just go from the beginning. First, thanks again to Redshift for allowing us to use their software. If we had a nice clear sky and there were no lights on, this is sort of what you'd see, without the labels, of course. Milky Way appears in the east at the horizon. It rises up, gets quite bright here because we're looking towards the center of the galaxy. Then it gets higher and higher in the sky. This is tonight, until it coincides with our Southern Cross and pointers, right? So they've got a background of stars from our own galaxy, and then it seems to come back down again. So it arches right across the sky at the moment and comes down almost west, just a little south of west. So it's quite amazing. We can also, at this time, providing you've got, again, not too much light in a southerly direction. You'll be able to see the other two galaxies close to us, the Large Magellanic Cloud and the Small Magellanic Cloud. We'll have a better look at them very shortly. Just quickly, let's go back towards the centre. Tonight wouldn't have been a good night because the moon is up there and it's about 3/4 full, so it is really fuzzing up the sky, makes it difficult to see a lot of this detail. But if we could magically get rid of that, we could see things like this. This is, is it that one? Hang on. Where's Sagittarius? There we are. Let's just see what that is and zoom in. And there we see it's the Lagoon Nebula. And over here we have the, hang on, get rid of that. This one here is the Triford Nebula, I believe it's called. Hang on, let's get a, come on, cooperate. I better zoom in, but there it is. This one here is the Triford Nebula. Also, a little bit to the right, you'll be able to see this one, which is a globular cluster, NGC 6544. Let's zoom in on that one briefly. There's a globular cluster. Now that one's about 20,000 light years away, and a little bit to its right there's another globular cluster, and this one is 9,000 light years away. Now that seems a lot, but our Milky Way is 100,000 light years across, so they're probably within the actual spiral arms, within the galaxy itself. And we're looking in that direction. This time of the year, we're looking towards the centre of the Milky Way galaxy. And there's the bulge of the centre right there. So this would be the centre here. Now, let's take a look at our galaxy from a, oh, just by the way, it's not too good looking at it tonight, certainly in Melbourne, but maybe on Monday night the weather will be a little bit better. And perhaps in a week or two's time when the moon isn't in the way, especially if you're on school holidays and you're away from the city, a great time to look at the Milky Way. And quickly in passing, you'll notice that Saturn has only just come up. Again, if you wait about an hour, that'll be a little bit further up in the sky. You can use the moon as a guide. And if you have a decent pair of binoculars, you'll be able to see Saturn tonight. Jupiter comes up about half an hour or so later. Let's now get on our spaceship and head out into space. And we'll go to the Milky Way. And we're going to show the area of Hipparchus. Hipparchus is apparently how it's pronounced. So we're heading out into space, and there's our Milky Way. And we're looking side on there. There it rolls over, and you can see that green area. It's not actually green, it's just showing us that's the region where the Earth is. Now, Redshift's graphics are all very, very good, but we can do even better than that. If Adam's ready, let's show you a picture that NASA has put together. It's the #1 one, Adam. And that shows you even more detail. Look at that, a roadmap to the Milky Way. This has been constructed from data collected by telescopes that are off the Earth, out in orbit around the Earth, out in space, where we don't have all the interference from Earth and from clouds and so on. And you can see there that it's a barred spiral galaxy. It doesn't just have a bulge in the middle. It's simple. It's a kind of a bar. And there are two main spiral arms coming out from it. But there are also some more diffuse spiral arms. And as Stuart explained, this is just how it looks at the moment. If we wait a couple of million years, those arms will look quite different because of the different speeds of all of the orbiting stars around the centre of the galaxy. If we have a look at the second one, it's the same image, but this time they've made it a map to show you where everything is. And you'll see the grid lines come out from the position of our sun and our solar system. And that gives you a pretty good idea of how it would look if we had a more detailed view of our own Milky Way galaxy from out in space. Now, remember, this is 100,000 light years across. So you have to get a fair way away to get the whole thing in. It's going to be a long time before we might manage to do that. It will require, I think, ability to travel faster than light. Otherwise, you're going to die of old age before you even leave the place. So we'll go back to redshift now. Thanks, Adam. And here we see our galaxy. Let's just turn it on its side. Hang on, we'll turn around a bit first. There we go. And if we turn it on the side, notice how that band of dark comes across here. This is because there is lots of gas and dust in our Milky Way, probably more than there is star matter. And you can also now, though, see the bulge at the centre. So the Milky Way is 100,000 light years across, but it's also 10,000 light years as the bulge in the middle there. So that's huge. It's also rotating. We're around here. When we were around the other side, so 180 degrees around there, we weren't around, not humans anyway. If we'd gone outside and got out of our time machine, you'd see dinosaurs wandering around the place when the Earth and the Sun were around that side of the Milky Way galaxy. So it's come this far in millions and millions and millions of years. So that seems to be really, really slow. Well, it's not. Remember, this is 100,000 light years across. So we've come 1.5 to 2 times that distance, probably, yeah, at least that distance since the time of the dinosaurs. And in fact, it's been calculated, we are in fact moving at 260 kilometres per second around the centre of the galaxy. So we're actually ripping through space. You'll hear some interesting statistics a little later when Merv talks about these things too. Let's just have a quick look now in the region around. There's a strange object there. What's that? Let's zoom out a bit. And if we get a bit further, look, there's those clouds we talked about, the large Magellanic Cloud and the small Magellanic Cloud. And if we just rotate the Milky Way a bit, you'll see where they are relative to us, right? They're at an angle below, but they're also apparently coming in towards the galaxy. Actually, it's in this direction. The large cloud is in the lead and the small cloud is following it. And apparently it's the first time, recent research has shown this is the first time it's actually come in, and it may either thud into our galaxy and merge with it, or it'll go flying past. But it'll certainly have an effect on us. But that's in about 2.5 billion years. Strictly speaking, they're our closest neighbours as galaxies concerned. The Large Magellanic Cloud is quite large. It's believed to also be a barred spiral, and it's just 160,000 light years away. So that's 100,000 light years. That's 160,000 light years. So it's pretty close, astronomically speaking. And it is, in fact, within the what did Stuart call it? Within that large sphere around the Milky Way. So it's actually part of that system. Let's just have a little look in closer to the Milky Way, and above the plane, there's Omega Centauri. What is Omega Centauri? Well, let's centre it quickly and have a look. We zoom in, and there it is. It's another globular cluster, like those other two we showed you in the Earth view. But this one, is, as you can see, is above the plane of the, of the galaxy. I'll just get back into the galaxy again. Sorry. Didn't do this before when I was rehearsing, did it? Sorry. There we are. And get rid of that. Get into here. There we are. Large Magellanic Cloud. All right. Oh, this is something new to me. I didn't know that was here before. Okay, we'll back off again. I don't know why it's done this. There we go. Oh, we're still within the galaxy, that's why. So let's go to this one and center it. And let's see if we can get away from, Oh goodness, excuse me. Let's just clear that back off. Okay, there's the Milky Way. Different view. Excuse me, folks. We're just going back to Earth. Bear with me. We'll go back to Earth, and then we'll go back out to the Milky Way again. This is just a little thing that happens when you have live telecasts. Back to Earth we go. All right. And back to Melbourne. All right, this is taking a little longer than we wanted. So let's go back again to the Milky Way galaxy. Just won't take long. Traveling faster than light speed. And here it comes. Zoom. Okay, there it is. All right, what we're going to do now, let's let it settle down. The Milky Way galaxy has a couple of galaxies nearby, and I think someone was asking about what are some of the closest galaxies to us. So let's have a look. There we go. And there's a large Magellanic Cloud. If we go around the other side, roughly in this plane, pretty soon something will come. Yeah, there's another galaxy there, the Andromeda Galaxy. This is 2.5 million light years away. When the light from the Andromeda Galaxy left there were no human beings. There were probably Neanderthals or ape-like creatures, but that's the Andromeda Galaxy. If we zoom in quickly, there it is. Not as good a picture as you saw with Ella, but there it is. So that's the Andromeda Galaxy. And the other one quite nearby is this one, which is about the same distance away, called the Triangulum Galaxy. And there it is. It's another spiral galaxy. Okay, so that's what it looks like out in space when we look at the Milky Way. There's our galaxy. All right, so let's go back to Earth. And, one quick point. The two globular clusters I was talking about, the early ones we saw from Earth are probably within the arm of the Milky Way. The other two, which is, let's move in, Omega Centauri and this other one, 47 Tucanae. There it is. Okay, there, as you can see, they are above and below the plane of the Milky Way. And that's because they've been thrown out in a recent, astronomically speaking, just a few million years ago, something large, possibly another galaxy, interacted with the Milky Way galaxy, and the forces that were happening there ejected those out of the Milky Way galaxy. Star clusters, globular star clusters within the galaxy don't last very long. They get cleaned up by the gas and dust in the galaxy. But the ones above and below, they're quite stable. They've been around for 10 billion years, and they'll probably be around for a lot longer because they haven't got all those influences working on. Okay, let's go back to Earth. And in through all those dense stars all around us, in through the solar system, the asteroids, there's our beloved planet, and back to Australia. And we're safe and sound on the ground. Let's go back to Petra. Thank you. Hope you enjoyed it. Looking forward to your questions.
Thank you, Andrew. Redshift is always so informative. Okay, up next we have Merv, and Merv will now explain what's beyond the Milky Way.
Cosmos fans, Mervyn here, and while tonight's topic is about galaxies, I thought I'd just let you know what is beyond our Milky Way in the way of galaxies. And just a reminder that the Milky Way is host to about 200 billion stars. On any clear night, in that yellow circle, you'll see 2,000 to 3,000 stars with your naked eye. But beyond the Milky Way, with naked eye, you can see 3 other galaxies. There's a large and small Magellanic Clouds to the south, and in the northern area you can see the Andromeda Galaxy in October, November time from Australia. The Milky Way and Andromeda and several other smaller galaxies are all what's known as the local group. In all, there are well over 40,000 smaller galaxies around the two major galaxies. And just to keep you awake at night, we are on a collision course. But don't lose any sleep over it. Our local group is not the limit. We are just part of the Virgo Cluster, and we lie a little way from the main Virgo Cluster. The Virgo Cluster has about 2,000 galaxies, and we, as a local group, are being pulled towards the main group. Is the Virgo Cluster the limit of our knowledge? No. The Virgo Cluster is part of the Virgo Supercluster. This is made up of about 100 groups of galaxies and clusters. It is not a rich supercluster, nor does it have a high-density core. So, what is a rich supercluster? The Lanakia Supercluster is home to the Milky Way local group, the Virgo Supercluster, and includes several other groups, clusters and superclusters of galaxies. The Lanakia Supercluster is reckoned to contain about 100,000 galaxies, with the densest region being the Centauri cluster. Lanakia is also home to a gravitational anomaly called the Great Attractor, which we are being pulled towards. It is in the region of the normal and shapely superclusters. Is the Lanakia Supercluster the limit? No. Zoom out further still and you'll find that we are part of the Pisces-Cetus supercluster complex. It's a superchain of superclusters, the Pisces-Cetus supercluster, the Pisces-Pegasus chain, and the Pisces supercluster. The Pegasus-Pisces chain, the Sculptor region, and the Sculptor supercluster, and the Hercules supercluster, and of course the Lanakia supercluster. But wait, there's more, a whole lot more. Our local supercluster is surrounded by a whole group of other superclusters. There's a Leo, Columbia, Sextans, Ursa Major, Corona Borealis, Hercules, Shapely, Pavoindus, and many, many more. They're all held together and interwoven through filaments, walls, and strings of galaxies with voids in between. The voids are like supersized soap bubbles, where the galaxies are forced around the walls to collect more densely at the junctions of the bubbles, or the voids. The local group of superclusters lie at the center of what is known as the observable universe. You've seen the Hubble Deep Field image that brings us views of galaxies 12 billion light years away. In the time it's taken the light from those galaxies to reach us, the universe has continued to expand at an increasing acceleration, placing those distant galaxies in the region of 40 plus billion light years away today. Speaking of Hubble, and bringing you back to the local Virgo cluster, Hubble, looking through the local Virgo cluster, lensed a galaxy cluster far, far away, the Able 1689. As well as being packed with galaxies, the Able 1689 is a host to a vast group of globular clusters. It's reckoned to be about 2.2 billion light years away. And finally, as you sit there in front of your media screen thinking your life is quite static, think again. The Earth is revolving on its axis, and the Earth is rotating around the Sun. The solar system is rotating within the galaxy, and the Milky Way and Andromeda are on a collision course. The local group is being pulled towards the Virgo cluster, and this is being pushed sideways by the local expanding void. Lanakia is being pulled towards the Great Attractor, and the whole complex is being pulled towards the Shapely Attractor, and pushed by a thing called the dipole repeller, which was discovered about 4 years ago. So, as I said, if you think your life is quite static, you're actually traveling in the region of 800 kilometers per second. the time it takes you to just clap your hands once and then clap them again. Good night.
Thanks, Merv. Whoa, there really is a lot beyond the Milky Way. Okay, please keep your comments coming. Drop them into the comments and we'll attempt to answer them. There is a planisphere to give away to the question of the night. And just a reminder, we're going to show a little video about why we would like you to donate to the Emerald SES.
Good evening, astro lovers, far and wide. Welcome to another night at the observatory. Tonight we're going to start the night at the observatory special a little bit differently. As you can see, we're out here at the Mount Dandenong Primary School, which was hit pretty hard with the storms that came through last week. We realised at Mount Burnett we were very lucky to get through the storm unharmed and unscathed, but many of our members were affected. They were without power, some still without power, and many people in the community are still heavily affected without access to things like clean running water. It's a terrible event, and even while we're out here today, it's pretty hard to sort of come to terms and actually believe what we're seeing. It's really like a natural disaster. So we wanted to start tonight by thinking about some of the ways that we might be able to give back to the community. And one of those ways is we're going to put a link up on the screen, and we'd love for you to make a donation if you can, big or small, to the Emerald SES. They do fantastic work. Unfortunately, one of their vehicles were damaged as part of the storms and in their response to those events last week. And they need that money for training and equipment. So if you can, we'd really appreciate it if you could, instead of donating to MBO tonight, make a little donation to them. We'd love to then give back to you for making a donation, and one of the ways that we're looking at doing that is by potentially setting up a COVID-safe night at the observatory in person. We'll get a few coffee trucks and maybe a donut van, so if you've got the ability to help us out with that, reach out via our Facebook or our email info@mbo.org.au. We'll get the community together, try and take our minds off some of the terrible things that have been going on. I know it's hard, but I think it's really important, and so does the rest of the team, to try and give back to the local community in whatever way we can. We're really sort of struggling to come to grips with it, and we're thinking of all of you, and hopefully these events that are going to come up will be a way of sort of getting back together as a community and taking the time to do that. So once again, if you can, make a donation and enjoy the rest of your night, and we'll see you soon.
All right, thank you for watching that, everyone. We now have Jamie showing you some information about the Hubble's deep field. Thank you, Jamie. The Hubble's journey so far has been amazing.
Yeah, it certainly has. I can't wait to see what the James Webb Telescope gives us. That's going to be absolutely incredible, Petra.
Yes, if it goes ahead in October, it will be amazing. Absolutely amazing.
Fingers crossed, eh?
Yes, fingers crossed this year. This year.
Yes, yes.
Thank you. All right. And finally, we have Steve speaking about a journey through space and time.
Thanks very much, Petra. I'll just share my screen here. Okay, well, hopefully you can all see that. And good evening, everyone. I just thought I'd take you on a journey through space and time to give you an idea about how we found the answer to what galaxies actually are. So when I was a kid, one of my early memories was of going outside at night and looking at the stars. I remember my grandmother was with me at the time, and I asked her why all the stars looked like a huge band of light that stretched across the sky. And she replied that she didn't really know, but it was called the Milky Way. Why was it called that, I asked. And she replied that it was called that because all the stars looked like spilt milk spread across the sky. But what was it, I wondered? Why did it appear like a large band of light stretching across the night sky? Where did all the stars come from, and will they always be there? So sometimes I think just how lucky we are that we are at last voyaging out into the universe and beginning to understand the answers to these sorts of questions. For hundreds and thousands of years, people from every culture have looked at the sky and they've wondered. For example, the Kung, Bushmen in Africa, thought that the band of light stretching across the night sky was an immense backbone that kept the sky from falling down. And Dreamtime stories of the indigenous people of Australia considered the Milky Way a vast river, with the dark patches running through it thought to be the banished spirit of a speared emu which had killed a blind man's wife. And the ancient Greeks thought that the diffuse band of light was milk spilt from the breast of the goddess Hera. Indeed, ancient Greek mythology is the reason why we call it the Milky Way to this day, and what is behind the origin of the word galaxy, which evolved from the Latin word Galaxies, which means Milky Way. But up until the last few hundred years, the stars were an impenetrable mystery to everyone. It's taken humanity 1,000,000 years of patient observing and thinking to get to where we are now, and of all of our insights about the stars have come from the instruments of science, which for astronomers are an open mind and a telescope. So how amazed must those early astronomers have been when they first started looking at the night sky through a telescope? All that milky stuff behind the stars turned out to be millions more stars, just very small and very far away. But they noticed many fuzzy blobs in the eyepieces of their primitive telescopes, and the more they looked, the more they found. Now here is a list of early objects catalogued by Charles Messier in the 18th century. The funny thing was not all of these objects were found within that familiar band of stars that you can see stretching across the night sky. They appeared to be all over the sky, and some looked very odd indeed. Rather than cloudy patches in the lens of the telescope, improvements in the resolving power of telescopes revealed that some of these objects had a distinct spiral shape, such as the Andromeda Nebula, which Ella spoke about earlier. Astronomers such as Heber Curtis in the early 20th century began to speculate that these spiral nebulae may actually be located outside of the Milky Way. However, other astronomers such as Howard Shapley thought that this was impossible. He thought that if the Andromeda Nebula was outside the Milky Way, it would have to be 2.5 million light years away, distances that astronomers back in those days just could not accept. Nonetheless, it seemed more and more obvious that the Milky Way had a spiral shape too, and appeared to stretch across the night sky like a thin band because we were staring through one of those spiral arms edge on. Now, the matter was finally put to rest by Edwin Hubble in 1925, when he looked at a type of star called a Seaford variable star. Now, this is a type of star that pulsates in terms of diameter and brightness in a very predictable manner, like what you can see here. By observing these stars in the early 1900s, an American astronomer called Henrietta Leavitt found that you could use these stars to accurately establish how far away it was. And Hubble found that the Seaford variable stars existed in the Andromeda Nebula. So using her discovery, he could demonstrate conclusively that the Andromeda Nebula was not a cloud of gas within our own galaxy, but an entirely separate galaxy with its own collection of stars located way outside of the Milky Way. The Andromeda Nebula has since been known as the Andromeda Galaxy, and in the 90 years or so since Hubble's discovery, we now know that there are literally hundreds of billions of galaxies in the universe. Now, the universe is much larger now than what we possibly could have imagined back when my grandmother was a young woman. Since I was a kid looking at the night sky, I've learnt that the sun is a star and that the stars we see at night are close by in our solar neighbourhood. I have learnt that the sun is part of the Milky Way and that the Milky Way is a galaxy with 100 billion stars, and that there are 100 billion other galaxies, each with hundreds of billions of stars of their own. My grandmother never knew that because much of this knowledge was completely unknown when she was growing up shortly after the First World War. I've also learnt that as we each try to make sense of the universe, we go from ignorance to knowledge, and that our individual growth reflects our advancement as a species. While we may sometimes wonder about who we are and where we are in all that immensity, what gives us our significance is our capacity to ask questions and our ability to reflect on the answers that we find. Therefore, the exploration of the cosmos represents not only a search for knowledge, but it represents a voyage of self-discovery. My grandmother has long since passed away, and now I'm a grandfather. It's my turn now to show my own grandchildren the wonders of the night sky, just like my grandmother unknowingly did for me when I was a child. When I reflect on this, I'm often reminded of a lovely poem by Wordsworth. For age is opportunity no less than youth itself, though in another dress. And as the evening twilight fades away, the sky is filled with stars, invisible by day. I hope that the presentations you've heard tonight will help inspire your own journey through space and time, and help keep that flame of self-discovery alight for generations to come. So thanks very much, and on with the show.
Thank you, Steve. It's amazing how a bit of curiosity opens a whole new discovery.
Indeed it is.
Okay, so that was the last of our speakers for this evening. Stick around for some brief notices before we head into questions and answers.
Hello everyone, we hope you are enjoying the stream. Coming up next is the question and answer segment, but first, some important messages. MBO is a volunteer-run organisation. If you'd like to support us, consider becoming a member, buying some MBO merch, or making a donation. You can find us on social media at these addresses. The live streams are created by a talented and diverse team. You can read the names of those involved below. Now it's time for Q&A.
Okay, welcome back. I now ask all and invite all our panelists to join me for the Q&A segment. Okay, hello everybody. Hello, welcome. Okay, for tonight's first question, and this one's for you, Jamie. Somebody by the name of Sebastian Burek from YouTube has asked, what's the likelihood that a side-on spiral galaxy is actually shaped as we see it? Or can you see the spiral shape when observed through a telescope?
So the shape of galaxies, it's basically how we see it from Earth. So the Andromeda, for instance, you saw photos of that before, and any other galaxies that we've seen, you know, there was a lot of images of different galaxies there on the video on the Hubble Deep Field. So all of those are categorized based on their shape, and that's just based on how we see them from here on Earth or from orbit around Earth.
Okay, great. Thanks, Jamie. Okay, so the next question will be for you, Stuart. And Adrian Martinez has asked, I was under the impression that the universe is expanding and accelerating. Then how is it possible to expect the Milky Way having a future collision with another galaxy?
Yeah, yeah. So those are either. Well, sorry. Yeah, the universe expanding happens on a much larger scale. Is the quick answer? Our galaxies are close enough together that the strength of gravity is able to pull us together, because gravity becomes weaker the further you are away from something. And because the universe is uniformly expanding, the more space you have in between you and something else, the faster you travel away from each other. So if something's twice as far away, if space expands, then it'll travel twice as fast away. Yeah. Also, I just wanted to touch on that. Whether things are gravitationally bound or how quickly they're moving away is partially how we determine what galaxies are in a cluster and how they're organized. We like to think of the local group and galaxy clusters as objects that are gravitationally bound. Those galaxies are going to stick together and be a happy family for the rest of time. On larger scales, they start to spread out, and that's where you get into the realm of superclusters. We don't think that all of the objects in our supercluster will stick by us. They're far enough away that they'll start to expand and fly away from us at quick speeds. Yeah.
Okay, brilliant. Thank you. While I've got you there, don't run away just yet, Stuart. I actually am interested in this question as well. So Massam has asked, is the sun moving clockwise or anti-clockwise around the Milky Way?
Yeah. So this one's a bit of matter of perspective. If you've got a rotating disk that looks like it's traveling counterclockwise, then you just have to look at it from underneath, and it looks like it's traveling clockwise. So it depends a bit on your perspective, and because we're within the disk, it's just how we define our perspective. We do have, we have Earth with a direction pointing north, and that vaguely connects with our idea of the solar system. It orbits in line with our ideas of north and south, so we can define. We usually define objects as traveling counterclockwise in the solar system because we look down from the north direction. But our plane of our solar system isn't in line with the plane of the galaxy that we're within. It's actually at a fairly extreme angle, actually. But we have arbitrarily kind of defined a galactic north that points out of the disk in one direction. And from that direction, we are traveling counterclockwise around the galaxy. So that's the answer. So it's a bit, due to perspective and definitions, we've defined it that way. But that's technically the answer.
Okay, brilliant. Thank you, Stuart. Okay, the next question is from Darian, who's 10 years old. And this one's for you, Murph. Darian's asked, if you went straight towards the center of the Milky Way by rocket, how quickly would you get there?
No, jolly interesting question, and I hope your maths is pretty good. Now, when you think the distance to the center of the galaxy is about 26,000 light years. So start multiplying that up, or down, depends which way you look at it, but 26,000 light years, you multiply that by the number of days in a year, by the number of hours in a day, and the number of seconds in an hour, and you've got an awfully big figure. It's about 6 and 15 zeros after it. Now, the fastest rocket we have got at the minute is one NASA is just developing at the minute, and they reckon it will do about 692,000 kilometers per hour. That's about 192,000 kilometers, sorry, 192 kilometers per second, which is pretty fast. So you combine that with the number of seconds or light seconds we are away from the center of the galaxy. And yeah, I haven't done the maths, but it's an awful lot of zeros. And if you're counting it in hours or days, I would still say you're in the region of about 15 and about 20 zeros after it, the number of years it would take you with the fastest rocket.
Whoa. Okay. Thank you, Merv. Okay.
But don't quote me on that.
Okay. All right. We won't. Okay. So the winner of tonight's questions, and I'm going to ask it now, and this one goes for you, Ella. It's from Stephen, who's 9 years old, and he's asked, what's the largest galaxy that we know of?
Well, congratulations on winning. It was an amazing question, and we've had such amazing questions tonight, so keep them coming along with all the streams that we have this year. So the biggest galaxy that we know of yet, and yet's the key word there because we're still discovering galaxies every single day, is called IC 1101, which is 50 times bigger than the Milky Way, and it's about 5.5 million light years across. Now, if you compare that to the Milky Way, our Milky Way is only 100,000 light years across. So that's a bit bigger, wouldn't you say?
That is big, yes. Okay, thank you, Ella, for answering Stephen's question. Yes, Stephen, you have won. Could you please get in contact us at prizes@mbo.org.au so we can send out your planisphere to you. Okay, so that on that note, that lovely note, and I'd like to say, yeah, no, the ticker's gone, Jackie. And on that lovely note, there it is. No, there it is. Thank you, Adam. Thank you, Adam. Make sure you send it to that email, prizes@mbo.org.au. I would like to thank you all tonight, my team as well as the public tonight, for being patient with all our technical problems that we had. In the end, the stream has worked out fantastic as always. And on that lovely note, the time has come to conclude tonight's show. Thank you all for joining us, and we all hope that you've enjoyed our program tonight about galaxies. If you have, please join us again for future shows, or you can rewatch any of our past segments on Facebook and YouTube. And don't forget to hit that like button or the little red subscribe button. Good night. Take care. And until next time, bye, everybody.